Swayam Prabha. Digital India. Educated India.
Welcome. In the previous lecture, we started our discussion on partial differential equations, and we considered the problem of hyperbolic equations. In this lecture, we will consider the two other types, that is parabolic and elliptic equations. So, we take this parabolic equation del u by del t is equal to c square into del 2 u, that is del square u, that is the Laplacian. Now, this Laplacian over u will give you a large term del 2 u by del x square plus del 2 u by del y square plus del 2 u by del z square. Now, in the particular case of one dimensional domain, only del 2 u by del x square will remain, and that gives us the one dimensional heat equation, which is this, right. Now, we do not go into the derivation of this differential equation governing the phenomenon of one dimensional heat equation or one dimensional diffusion, because in the chapter on vector calculus, in chapter 18, you might have already encountered, you might have already got familiar with the derivation of this equation through one of the exercises. So, we take this heat equation now and try to see how we solve this for given initial and boundary conditions. Note here that the time derivative in this equation is involved only up to the first derivative, that is, it is a first order differential equation in time, although in the space variable it is second order differential equation. So, for x it will need two boundary conditions at x equal to 0 and x equal to L. On the other hand, for time there will be only one initial condition that will be required, and that is the initial value of the function that is here at all x. This is the only initial condition that is needed, value of the function, because second derivative is not involved in the differential equation, only first derivative is involved. Okay. So, this is a complete description of the initial value problem, in which these are the boundary conditions and this is the initial condition. Now, in this case also, to try to solve this differential equation with the method of separation of variables, we will assume a solution of this type, in which the two variables are separated. The function u is expressed in the form of a function of x only multiplied with a function of t only, and then we construct the first order derivative with respect to t, that will be x t prime, and that will put here, and then the second order derivative with respect to x, that will be x double prime into t, that will put here, and then we get this differential equation. Okay. And here, as we divide this entire equation both sides with c square x t, then here x will get cancelled and c square t will come in the denominator. Here c square t will get cancelled and x will come in the denominator. Now, you see that the left side is a function of t only and the right side is a function of x only. So, variables are separated. So, we equate both of these, that is each of these, to a constant. Again, the boundary conditions over x will require this constant to be negative, because we want the solution to be 0 at x equal to 0 and return back to 0 at x equal to L. So, we will need this negative constant, so that the result comes in terms of sinusoids rather than exponential. So, then when we separate the, so with this negative constant here, we separate the variables and get these two differential equations. This is a second order ODE and this is a first order ODE. linked together through the common value of p. We first consider this differential equation, the solution of which we constructed in the last problem also, and that is this for all values of n equal to 1, 2, 3 and so on. And the corresponding value of p, that is n pi by l, we take, and then the other equation gives us here Cp. So, Cp whole square. So, lambda n is Cp. So, when we put that, we get the solution for t, which is capital T, which is even simpler because that is a first order differential equation. So, we get this exponential solution, and then every product of this and this for every value of n will be a solution, and their linear combination is also a solution. That will be the complete solution found through superposition, and this solution will satisfy the boundary conditions because each and every component of it satisfies the boundary condition, and this will certainly satisfy the differential equation also. Now, only required thing is to find the coefficient a n, a1, a2, a3, a4, and that we find by applying the initial condition. So, as we apply the initial condition, we find that we get this, which happens to be the Fourier sine series of the function f, which is the initial distribution of u over x. And as you see that in time, this is an exponentially decaying term, okay, and therefore, as enough time elapses, as t tends to infinity, we will find that this tends to 0, and that means the steady state solution of the problem is, that is, after a lot of time elapses, the steady state will be reached in which the entire solution will be 0, and that makes direct sense from the physics of the problem, in which both the endpoints are maintained at 0 temperature and there is no heat source in between. So, that means that whatever non-zero temperature values were there earlier initially over the rod or bar, so that higher temperature will reduce, and that will happen through heat transfer through the boundary. Okay. Similarly, if the interior temperature is lower, then from the outside of the system heat will be taken in and the entire rod will reach 0 temperature after enough time has passed. So, this is the solution of the problem with t tends to infinity, this entire thing will become 0 all over x. Now, in this particular case we had homogeneous boundary conditions. Now, if the boundary condition is non-homogeneous, in that case we will find that, say, suppose at x equal to 0, this is the condition, at x equal to L the condition is u2. Even if u1 and u2 are not 0, but equal, the previous solution will still be applicable, because the entire temperature scale will basically rise and the rest of the thing will be same. On the other hand, if u1 and u2 are not same, if they are unequal, that is, the two endpoints are maintained at different temperature values, in that case we will find that the boundary conditions do not separate when we try to apply the separation of variables, and that kind of a situation stops the problem from being a separable problem directly, and in that case we try to apply a little adjustment, and in the adjustment we say that we assume the solution as a sum of two terms, capital U plus USS. This subscript SS refers to steady state, in which we say that this component capital U satisfies the homogeneous boundary conditions, that is 0 boundary condition at both ends, okay, and it satisfies the differential equation also. On the other hand, this satisfies the boundary conditions. So, then this component, as we differentiate it and put inside this, so del u by del t will be equal to del capital U by del t, because this does not depend on t. So, that we put here, and the x derivative, second x derivative of this will be del 2 u by del x square that is del 2 capital U by del x square plus the second derivative of this, and then we say that we will be able to separate the variables if this does not enter into the differential equation at all, that is if this fellow's second derivative turns out to be 0. So, the second derivative of this is 0 and it satisfies the boundary conditions. This will give us a boundary value problem on of the ordinary differential equation. Okay. That is, this is the ordinary differential equation, that is second order ordinary differential equation in which the second order derivative is 0. That means the solution is linear function of x, and the linear function of x to satisfy these two boundary conditions must be this. So, this is the USSX component, that is the steady state solution, and the rest, which is the transient solution, when we put back we find that that will satisfy the earlier boundary value problem, initial boundary value problem with the homogeneous boundary conditions, that is this, which we have studied. So, here in the place of f x, which is the initial value of small u, we will have the f x minus USS, which is the initial value of capital U, and this change in the initial condition with the other homogeneous boundary conditions and this differential equation will give us the same solution which we found earlier, and that solution we compose with the steady state solution and get this complete solution. Now, the steady state solution will be this, which will remain after enough time has passed, and this will be the transient component. Okay. And in this case the coefficients Bn will be found from the Fourier sine series of not f x, but f x minus USS. Another particular case we can consider, and that is the problem of the same heat conduction problem, but not over a finite rod, not over a finite domain, but over an infinite wire. For example, this is suppose the infinite wire, and in this case we will not need any boundary condition, because the infinite wire will have no boundary. We are trying to find out solutions which are bounded, that is all. So, over the infinite domain. So, this is a differential equation only with an initial condition, there is no boundary. So, there is no boundary condition. So, in place of n pi by L, now we will have continuous frequency variable p, and rather than finding the solutions of solutions in the form of a sum of discrete components, we will find the components now are continuous. So, therefore, the summation will be replaced by an integral. Okay. So, earlier we had sigma u n, now we will have integral of u p over d p, that is the d p is the differential of the frequency variable p, and the solution u p in a similar manner as we found in the case of Fourier series, here we will get the corresponding Fourier integral. So, that is the term here which earlier we equated with the Fourier series, now will be a Fourier integral, in which the Fourier integral coefficients will be found in the usual manner. Now, if we combine these two and put here, you can also put this entire term in the form of the cosine of px minus pv, that kind of a term you can put here if you insert these ap and bp expressions here. So, the whatever role in the earlier finite case was being played by a Fourier series, now will be played by Fourier integral, and everything else remains same with the appropriate changes. So, the frequencies will be now continuous, and these ap and bp, the coefficients will be determined through these integrals. Alternatively, in the case of infinite wire, rather than using Fourier integral, one can also attempt the solution with the help of a Fourier transform, and the way to do that is this. We first use the derivative formula of Fourier transform, and with respect to one of the variables, in this case x, we apply Fourier transform. So, here we on the left side we have to apply the Fourier transform of ut. Now, derivative is with respect to the variable t, and Fourier transform we are taking with respect to variable x. Since these two variables are independent, then we can change the order of differentiation and integration. Note that the Fourier transform basically involves an integration. Okay. So, the Fourier transform of derivative with respect to t is this, okay, which will be the same as the time derivative of the Fourier transform. Okay. On this side, the derivative is with respect to x and the Fourier transform is also taken with respect to x. So, we use the derivative formula of Fourier transform, that is the Fourier transform of the derivative is IW into Fourier transform of the original function. So, second derivative, so twice derivative formula has to be applied, so IW whole square, and then this is u hat, that is the Fourier transform of u. Then this differential equation that we have got is a first order differential equation with respect to time in the function u hat, that is Fourier transform of u with respect to x. That is, we have converted this differential equation, partial differential equation, to an ordinary differential equation of the Fourier transform of u with respect to x. Now, the initial value problem we can construct by taking the Fourier transform of the initial value function also, that is both sides we take Fourier transform, and that gives us the initial value of the Fourier transform. So, as we take the Fourier transform here, so we get u hat at time equal to 0 as f hat of w. So, that means for this differential equation, which is a first order differential equation, we have got this initial condition. Okay. So, this differential equation with this initial condition, first order differential equation. So, the solution is very easy. So, we get this solution. Okay. This is the solution of this first order differential equation with this initial value. Therefore, it is appearing here. And then we say that after we have got the solution, now we take the inverse Fourier transform of this. And inverse Fourier transform will give us this one from the directly from the formula, that is f hat into e to the power minus c square omega square w square t into e to the power I w x integrated over w from minus infinity to plus infinity, which if we put this here, then we can put it in this form, and we have actually expressed the solution in the form of quadrature, and this same solution we would get from the Fourier integral representation also. Now, how this integral, how this quadrature is to be evaluated, that we will consider a few lectures later after we have studied complex analysis also. Currently, we proceed to the discussion of the third type of differential equations that we are going to handle here, and that is the elliptic equations. The same heat flow equation that we have been discussing, that is del u by del t is equal to c square into Laplacian of u. So, in that the Laplacian involves del 2 u by del x square plus del 2 u by del y square plus del 2 u by del z square. Till now we have been discussing one dimensional problem. Now, let us take a two dimensional heat flow problem. Okay. So, if you consider the heat flow in a plate, so the entire boundary of the plate will require boundary conditions. Okay. So, this will give us the two dimensional heat equation in this manner, right. And then you say that for this particular problem, we consider that enough time has passed and we want to find out the final steady state temperature distribution over the entire plate if we prescribe conditions, appropriate conditions over the boundary of the plate. Okay. So, then if enough time has been elapsed and the temperature distribution has reached a steady state, that means del u by del t will be 0, and then we get this equal to 0, and this is a Laplace equation. The Laplace equation is an elliptic equation. Note that in this particular case, the original equation, this is actually a parabolic equation in time and space variables. In time you have got this first order derivative, in space variables you have got this term. So, between time and space you had the parabolic nature of the differential equation, but after the steady state has been accomplished, this time derivative gets removed from the differential equation, and then what remains among the space variables, it is elliptic. Now, when we try to solve this Laplace equation, this elliptic equation, Then if we apply the separation of variables method over the boundary problem of this for a rectangular plate to keep things simple. Now, in this rectangular plate, the three sides of the rectangle, that is x equal to 0, that is left side, x equal to a, that is right side, and y equal to 0, that is bottom, and y equal to b, that is this is one boundary, this is another boundary, this is third boundary, and this is the fourth boundary. Okay. So, over this boundary, if we prescribe the temperature values over the entire boundary, then we have got a Dirichlet problem, right. So, this is the differential equation and boundary conditions are here. Now, notice that on three sides we are applying 0 boundary conditions, okay, for this particular case. It could be different. On the fourth side, we are applying an arbitrary boundary condition in the form of a function f x. Now, if this also is 0, then we know what is the solution. Then the only solution possible is overall 0. Okay. So, therefore, to make it a non-trivial problem, we are applying an arbitrary boundary condition on the fourth boundary. So, we have got the Dirichlet problem over this rectangular domain, that is here. As we apply the separation of variable technique, that is as we try to apply, we start with this proposal, and the second order x derivative of this, that is here, this one, will give us x double prime into y, and del 2 u by del y square will give us x y double prime. So, this we get, and then overall as we take this on the other side of the equation and divide throughout with x y, then we get this equal to this. So, variable separation has succeeded. This is dependent only on x, this is dependent only on y, and then as we equate it to a constant, why negative in this case? Because we want the x equation to have periodic solution, that is starting from 0 should come back to 0, because at x equal to 0 and x equal to a, the value is 0. For y, such a conversion is not there. Okay. So, therefore, the x solution we want to be periodic, and therefore, we take a negative constant here. Corresponding y solution will be exponential. So, then we separate the two ODEs, get this and this. Now, the solution of this will have sine and cosine terms, it will be periodic. The solution of this will be exponential. So, then this boundary conditions we have been seeing for quite some time. In the previous lecture also we saw this. So, then this gives us the solution which is the same as earlier cases, sin n pi x by a. Now, this one either you can write the solution of this in terms of e to the power py and e to the power minus py, or you can write in terms of hyperbolic cosine and hyperbolic sine. That is obvious that the two are equivalent, because hyperbolic cosine is nothing but e to the power y plus e to the power minus y py by 2, and similarly sine hyperbolic will have a minus sign here. Okay. So, since we are talking about linear combination of the two, so whether we talk in terms of two exponential functions or sine hyperbolic and cos hyperbolic, result is equivalent. Okay. So, now with this yn and this xn, when we put them together back into the proposal, then every xn into yn will be a solution of the differential equation, each of them satisfying the boundary conditions. And so, the infinite sum of such products, this kind of products will give us a solution in which the initial condition, that is y of 0 equal to 0, that we get from here, that is as we put small y equal to 0 in the initial not initial condition, boundary condition here, as we put small y equal to 0 here, we get u equal to 0. So, that means in the proposal the corresponding capital Y has to be 0. So, that gives us a n equal to 0, that means this part goes off, because sine hyperbolic is anyway 0. So, a n coefficient has to be 0. So, that gives us only this term. Okay. So, then we have got the solution here like this. So, the complete solution will be an infinite sum of such terms for n equal to 1, 2, 3, 4 and so on, that is this. Only remaining thing now is the determination of these coefficients b n, and that we do by imposition of the last boundary condition, that is over this boundary y equal to b. So, as we impose that condition, we get the this as a constant and that value into b n into sine of this. So, that gives us Fourier series. So, that means, as we apply this last boundary condition, we get the coefficients b n in terms of the coefficients of the Fourier sine series of the function f x, and that completes the solution. So, in this particular case, we found that the boundary conditions on the three sides were homogeneous. That helps us a little. That is, finally, we had to crack only one Fourier series. On the other hand, if the boundary conditions over all the four sides are non-trivial, then we can split the problem into four different parts. In each of the parts, one boundary condition is taken as non-trivial, others are 0, and then finally, when we combine the four solutions, we get the complete solution, we get the correct solution. Now, till now we have seen cases where the differential equation is separable, but the boundary conditions are not. Sometimes boundary conditions are not separable, and then we took the steady state solution separately and constructed a solution. There could be also situations where the differential equation itself is not separable. For example, if there is a heat generation in the same problem, then you may get a phi x y like this. Okay. That is, Laplace equation will change to Poisson equation if rather than 0 on the right side you have got a function of x y. Even a constant will create a problem with the separation of variables. In this case, the variables will not be possible to be separated. So, separation of variables will be impossible with a non-zero term here. So, while solving the Poisson's equation, we need to do something else, something more. So, for that we can construct the solution in two steps. We consider a solution in this manner, in which we have got a UH component, which is actually the solution of the corresponding Laplace equation del 2u equal to 0, and take a UP, a particular solution of this differential equation. Okay. And then the way we solve the ordinary differential equations as summing up the complementary function and particular integral, particular solution, in that manner we can find the solution of this Poisson equation. For that, the sequence of steps is also important. In this case, in the solution of Poisson equation, we first find out a particular solution of this differential equation by some method, by some means. That is, if we can find one solution of this which perhaps does not satisfy the boundary conditions, then we keep that, and after finding that particular solution, which most probably does not satisfy all of the boundary conditions, maybe does not satisfy any of the boundary conditions, but still that having a solution of the differential equation itself helps, because then we consider the solution of this Laplace equation for UH in such a manner that UH plus UP together satisfies the boundary conditions. Then UH plus UP together, this proposal satisfies the boundary condition, and UH satisfies del 2u equal to 0 and UP satisfies del 2u equal to phi, and that means the sum will satisfy del 2u equal to phi. So, in this manner, if we can get hold of one solution of the Poisson equation, even if it does not satisfy the boundary conditions, it will be good, because using that solution we will apply the boundary condition on UH appropriately. So, that whatever boundary conditions UP gives, that component gives, the other component UH, which is in our hand, which we know how to solve with homogeneous boundary conditions. So, we find out that what boundary conditions UH should satisfy, which will satisfy the given boundary conditions and also compensate for the boundary values of UP. So, that way we can construct the solution of a boundary value problem of this also. So, in this case only separation of variable did not help, but through one particular solution we could reduce the rest of the job to the solution of a Laplacian equation, that is this. So, one example in the textbook that we are considering illustrates this particular situation. As our next example, let us consider a 3 variable problem. Till now all problems that we have considered have been 2 variable problems. Suppose we have got a rectangular membrane, rectangular because we want to keep the discussion simple, okay. Otherwise the member could be of any shape. So, for a rectangular membrane, suppose the boundary, the rectangular boundary of it is bound and fixed, and then the membrane can vibrate, okay. So, earlier we have seen that the one dimensional analog of this, the one dimensional version of that is the vibration of string problem, okay, in which we had del 2 u by del t square equal to c square del 2 u by del x square, that is all. Now, rather than a string which is a one dimensional medium, now we have got a membrane which is a 2 dimensional entity, 2 dimensional domain. So, we have got this. Now, this equation is actually a hyperbolic equation, as any vibration problem will entail. When we say that it is a hyperbolic equation, we mean that hyperbolic nature is manifest between the time and the space variables, that is between this and this, it is a hyperbolic relationship. So, the Cauchy problem of the membrane will be this, that is the differential equation along with these initial conditions, initial position over the entire xy domain and initial velocity over the entire xy domain, and these will be the boundary conditions u at u 0 y t, that is at x equal to 0, x equal to a, then y equal to 0, y equal to b, this same rectangular domain. Over this rectangular domain around the boundary we have got these boundary conditions. Now, how to solve this particular initial boundary value problem? So, first we try to separate the time variable from the space variables. So, for that we propose a function of x y of the space variables multiplied with a function of time variable only. In this manner we propose a solution in this manner. Now, as we propose this solution and affect the differentiations, so this will be the del 2 f by del x square, that derivative, that is f x x. This will be f y y, that is this will be f x x into t, and this will be f y y into t, okay. And here this will be f into t prime t double prime, that is second order derivative with respect to small t. So, then we will have this differential equation as f t double prime is equal to c square into f x x t plus f y y t. Now, to separate the variables x y from the variable t, overall we will have to divide with f and t, and if we want with c square also. And as we do that, then here we will get, as we are dividing with c square f t, so c square will go off, t will go off, f will come in the denominator. So, f x x plus f y y by f, so that is here. On this side f will go off and c square t will come in the denominator, that is here. Now, again we say that this side depends only on the space variables and this side depends only on the time variable. Now, for both of them to be equal, they have to be equal to a constant. What kind of a constant? So, for answering this, what kind of a constant, we will again see that if we take a positive constant here, then f x x plus f y y minus that positive constant into f will come, and that will require that in space the solution increases continuously or decreases continuously, and in that case this kind of homogeneous conditions the boundary will not be able to fulfill. Therefore, here we need a negative constant. So, we put minus lambda square. As we put minus lambda square, then this equal to minus lambda square will give us this equation, because f will go here, minus lambda square brought on this side of the equation, it will give us fxx plus fyy plus lambda square f equal to 0, and this differential equation will give us the periodic sinusoidal solution of x and y, which will be able to satisfy these boundary conditions, right. This equation is called the Helmholtz equation. The other part will give an equation in the function capital T. First, we consider this. This is again a partial differential equation, because it has got two independent variables involved, x and y. Note that from this differential equation, as we applied separation of variables between time and space variables, so this time variable was separated in the other differential equation that we will get, and this is an equation in the space variables only, and among the space variables this happens to be an elliptic equation. In this elliptic equation involving the space variables only, we apply one more round of separation of variables, and for that we assume fxy in this manner. As we do that, the first term fxx will involve x double prime into y, this will involve x into y double prime. So, we can write this in this manner, x double prime into y plus x into y double prime plus lambda square f, which is xy equal to 0. Now, in order to separate x and y terms, we can do it in several ways. So, one possible way to do it is to divide overall with xy, okay, capital X capital Y. So, as we do that, from here y will go off, x will appear here, from here x will go off, y will appear here, and from here both will go off. Okay. So, we will get this, right, and then we can take these two terms on the other side, or we can take only this term on the other side. So, suppose we take both of these terms on the other side of the equation, and then we will get this entire term minus y double prime plus lambda square y by y. Okay. So, this whole thing depends only on y component, and this depends only on x component. So, this again we want to equate to a constant, and here again this equated to the constant of separation will give us a straightforward differential equation in x, which we have earlier also seen, and that will have x double prime plus mu square equal to x, and therefore, this is necessary to be taken as a negative constant minus mu square, because otherwise in x the solution would not come back to 0. On the other side, when we equate these two, we find that negative sign gets cancelled, and we get y double prime plus lambda square y equal to mu square y. That means, y double prime plus lambda square minus mu square into y, and that lambda square minus mu square has been mentioned, has been denoted here as nu square, which basically gives us a representation of lambda in terms of mu and nu. That is, the lambda that we chose here now gets represented in terms of the two new constants mu and nu that we are choosing now. So, in mu and nu, that is in capital X and capital Y, the two differential equations are similar, and for the those with homogeneous 0 boundary conditions, we know the solutions already, and we construct those solutions. These homogeneous boundary conditions over x and y, which we derive from the homogeneous boundary conditions given for the variable the function u itself, we get the solutions in this manner, right. So, we find that mu equal to m pi by a will give us solutions for x, nu equal to n pi by b will give us solutions for y, and for every value of m and n, that mu and that nu will give us different solutions for xm and yn, and corresponding value of lambda will be found from here, that is mu square plus nu square under root. So, that is for every value of m and for every value of n we will get a value of lambda. That means, we take large number of m equal to 1, 2, 3, 4 and n equal to 1, 2, 3, 4, then for that we will get a set of 16 values of lambda, lambda 1 1, lambda 1 2, lambda 1 3 and so on. Okay. So, for every pair of values of m and n we will get a value of lambda. Corresponding lambda will give us from here the corresponding differential equation for the function t of time, and that will be t double prime plus c square lambda square capital T, that is this t double prime plus c square lambda square capital T equal to 0. Now, we know the solution of this also will be found in this manner itself, but here we write the complete solution, because on this it is time variable involved and we do not have so straightforward boundary conditions as we had in the case of x and y conditions. So, here we write the complete solution in terms of lambda mn and coefficients a mn b mn. Okay. That means, for every pair of values of m and n we will get coefficients, different coefficients here corresponding to different lambda mn values. So, this will be denoted as t mn. Now, we find that xm of x into yn of y and corresponding tmn of t, the product of these three terms will give us one solution of the original differential equation that will satisfy the differential equation and all the boundary conditions. So, we get the complete solution through superposition of all these solutions for different values of m and different values of n. That means, we get the solution in the form of this double summation. The outer summation is with respect to m, the inner summation has been shown with respect to n. So, this is t of t, this is, that is tmn of t, this is xm of small x, this is yn of small y. This is the complete solution which will satisfy all the boundary conditions and certainly the differential equation. Now, as we put the initial conditions, we put t equal to 0. So, at t equal to 0, this sine term will vanish and we will get a mn, this cosine will be 1. So, a mn sine m pi x by a into sine n pi y by b, that is this, which will be the initial configuration of the membrane that is given. And when we differentiate it, then this will give us sine, and upon substitution of t equal to 0, that will be 0, and this will give us cos along with a coefficient c lambda mn, that is here, and upon substitution of value t equal to 0, that cosine will be 1. That means, c lambda mn into b mn into sine and sine, that will be equal to the initial velocity of every particle over the membrane, that is for all values of x and y. So, now you find that the coefficients a mn and b mn can be found from the coefficients of the double Fourier series of fxy and gxy. Okay. One simple case of this is given in the exercises, in which case you then go ahead and continue to find the values of a mn and b mn from expansion of the Fourier series of the initial condition functions. Now, if other than this rectangular domain, the domain is of some other shape, so then you find that sometimes the differential equations that you get are not so straightforward, in which case we get the solutions by solving a simple solution like x double prime plus lambda square x kind of things. But for domains of circular symmetry, which is important in many practical systems, say cylinder. Okay. In the case of cylindrical domain, quite often we find that the BVP that we construct gets modeled more conveniently in terms of cylindrical polar coordinates. Okay. And sometimes in domains which are spherical in shape, we similarly use spherical coordinates. So, use of cylindrical polar coordinates and spherical polar coordinates quite often leads to individual separated equations in the form of Bessel's equation or Legendre equation. And in that case, the component ODE that we solve to find out the solution with respect to one of the variables turns out to involve the Bessel function and Legendre functions also. So, depending upon the shape of the domain, you may find that the solution of the resulting ordinary differential equation, that is resulting from the process of separation of variable, may turn out to be the straightforward differential equation that we have been solving with constant coefficients, or depending upon the shape of the domain with circular symmetry, quite often Bessel's equation or Legendre equation also evolve, and that actually is the starting point of the study of Bessel's equation and Legendre equation in the ODEs. So, now that we have already discussed the series solutions and Bessel's polynomials, so these, since we have already studied the series solutions of ordinary differential equations, and we are already acquainted with the Bessel's function as arising out of this kind of equation, and Legendre polynomial as arising out of the solution of this kind of equations. So, as we consider such symmetries, circular symmetries, we can get the component solutions and construct the complete solution, and then apply the initial conditions to these situations also. In the exercises in the textbook in this chapter, you will find some examples which involve such cases. However, if the domain in the xy plane or the xyz space does not have any such symmetries, neither rectangular nor cylindrical nor spherical, then, that is, if the domain is general shape, in that case such analytical solution will not be possible, and in that case typically we try to solve the differential equation with the help of numerical means. And numerical solution of partial differential equations is in itself a large topic, and then we do not go into that as part of this course. So, let us summarize at this point what are the things that we have discussed in these two lectures on partial differential equations. First is that the partial differential equations appear in several physically relevant contexts, and some of the very important governing equations of phenomena we have tried to study through some analytical solutions with the help of Fourier series, Fourier integral, and Fourier transform based solutions through the method of separation of variables. In that, we have discussed the initial and boundary conditions, their meanings, and their different situations in the different kinds of problems that we apply them, and we have studied the separation of variables method. And examples of such boundary value problems or initial boundary value problems with hyperbolic, parabolic, and elliptic equations of a few cases we have discussed. In some cases, we have conducted the modeling and then the solution, and then interpreted the solutions in these two lectures. And in the last example, in the case of two-dimensional membrane problem, we have also seen one particular case of cascaded application of the same separation of variables twice. In the case of a three variable problem, the first application of the separation of variables technique produces one ordinary differential equation in one variable and another new partial differential equation in two variables. A second application of the same separation of variables over this partial differential equation splits the equation into three different differential equations, that is complete separation. And that kind of a cascaded separation of three variables will finally involve a double Fourier series for the determination of the coefficients, the Fourier coefficients. Now, this gives us a very brief overview of the partial differential equations which appear most often in practical situations. And in the course, as we have throughout tried to emphasize on interconnections of several different areas of applied mathematics, this particular topic puts those interconnections in a very intricate manner, and some of the solutions which we have got here will be completely reduced after we develop some integrals based on the theory of complex analysis. And our next module of this course is on the complex analysis. In that, we will have next 3 lectures devoted to the area of complex analysis, and after the third of those 3 lectures, we will develop some tools by which we develop quadrature formulae for some of the integrals that appear as a result of the solution process of some of the partial differential equations that we have studied in this lecture. So, next lecture we start with the first topic of complex analysis, and that is the topic of analytic functions. Thank you.